Aluminum fluoride is made industrially by reacting aluminum oxide hydrogen, right? So basically the equation, that's all I care, right? Balance state symbols all in, I say, ooh la la, you're mine, okay? Calculate the standard enthalpy change of this particular reaction when you're given what? When you're given the formation enthalpy of 1, 2, 3, 4, everything out. They want you to calculate standard enthalpy change of reaction. You have a few ways. The first one, energy cycle. I'm not going to draw in exam. All right, you finish your exam, right? So now we discuss, all right? Those cannot finish your paper or you realize, shit, how come almost all the subjects, especially chemistry, cannot finish the question? It's because you take your own sweet time and therefore also your presentation, you write too much. You need to go fast. A, I am not going to draw energy cycle. I saw formation enthalpy, you ask me for reaction enthalpy, directly come out the formula. Make sense? Don't waste time. Because some people say, Mr. Chua, yeah, my school always use cycle, no? Then draw lah. And you know it's better. I never say it's wrong. I say you're too slow. In exam, you suffer. And in exam, do I even write this out? I don't. Everyone okay? I directly calculate out. I put the values in and I sort it out, done a long time ago. All right, so what's the product? This side is the product. So I will just show this second line onwards, straight to the point. All right, minus 1504. The AL or ALF3, right? I'm going to use this value. How many? 2 moles. Plus 3 water. Where's the water? Or steam? 3 minus 242. All right, use as many brackets as you want so that you don't get sabotaged by the negative sign. And the product side, who is it? I mean the reactant side, ALO3, this one, negative 1676 plus 6 HF. So it's 6 of negative 271. So it's minus 432 kilojoules per mole. Right? Nothing much. It's just calculation. All right. So again, don't draw if you have a chance not to draw. And a standard question will, after you have a delta H, they will somehow link it to delta G most of the time. So the next part, they say, hey, the delta S value is this value. And ask you to explain the significance of the sign. What sign? This sign, which is negative. All right. So part B, we will say the delta S is negative, implies or means that, or shows that the system becomes less random. A lot of us will just end our statement here. I will apply back to the question to play safe, which we learn is all about the mole of gases. 6 moles of gases become 3 moles of gases. Okay, I will continue right. This occurs something like that because there is a decrease in the number of moles of gases. You want to put the value? Carry on. All right, so I'll go and talk about it. Okay, so I always go back to the question. And part C, as mentioned, is quite typical. They want you to calculate delta G. So delta GR theta equal to delta HR theta, right? Minus T delta S R theta. You have all the values. All you need is just be careful of your units. Delta H you calculated was here, minus 432. Both of them are kilojoules, right? I saw it's kilojoules. I'll leave it as kilojoules. Nothing wrong with it. Just make sure they are the same unit, right? Temperature 298 cos theta, and this minus 0.39. So my delta G will be in terms of kilojoules now. Kilojoules per mole, right? So minus 316 kilojoules per mole. All right, I'll get 1 mark for this basic calculation. I'll take it, which usually is to lead you to the next part. How will the value of the delta G for this reaction change with temperature? Right. So this is a question. How will the value of delta G for this reaction change with temperature? And after that, what consequence will this have for the condition used to make ALF3 industrially, which is this one? Are we using the value? I'm not using the value. Instead, I am using the sign. right? So a lot of people get confused. What's the value? The value has no meaning to me. Make sense? What I'm interested is actually the equation, which we know that delta S is negative. Delta H we calculated is negative. So this is positive. So how will it be affected with the change in temperature? Up to you whether it's increase or decrease temperature. Normally I like to talk about increased temperature. When you increase the temperature over here, as you can see, therefore this will become more positive. Make sense? Therefore that's not good. Correct? So my delta G will become more and more positive. So that will therefore be my answer. As we increase the temperature, delta G, Gibbs free energy change, will become less negative, or you can say more positive. It's the same English word. So I have answered this part. And then we apply to the question. What consequences will this have for the condition used to make AlF3 industrially? So if you're the engineer or the chemist and your boss, can we keep heating it up? Now, this is where we link to the next topic called kinetics. Remember, in a chemical reaction, you need to consider two factors, correct? It must be kinetically feasible and energetically feasible. Since Sec 3, Sec 4, or in fact, Sec 1, Sec 2, we all know by increasing temperature, your kinetic energy will increase. Make sense? So your reaction, it will always be faster. Make sense? So which next topic we'll discuss. So if your boss tell you, hey, I want it to be done in 1 week rather than 1 month, can you keep increasing temperature from 100 degrees Celsius to 300 degrees Celsius? What do you mean for this reaction? Imagine your boss sells this, you work in this plant, right? So you'll be doing this calculation and to tell your boss, say, yeah, you know, you shorten the time to get the product by 75% or something like that, right? Very fast. But you know what? No good, leh. What do you mean by no good? Because by doing so, increasing temperature, you become less and less spontaneous. And there is therefore a chance that it becomes what? Energetically infeasible. Make sense? So that's our answer. That's it. All right. So therefore, the temperature should not be too high. You can also keep it as low as possible because low, the rate is slow. I'm going to sack you at the same time. All right. You can say you increase temperature, but cannot be too high, boss. Then I ask you what temperature, then you go calculate. All right. Temperature should not be too high, else it will not be spontaneous anymore. So imagine you do a very high one, then suddenly no product come out. Or you do a very low one, how can I wait for a few months and still no product come out? Right? It's always this. So next topic, when we go to kinetics, we will come back, whereby the last part, the answer is about energetics. Are you with me? If you would like to catch my latest videos, click on subscribe button right now. And click on the bell if you want to receive instant notifications once I've uploaded my latest video. If you would like to join my live chemistry classes and revision workshops, go on to winnerseducation.com and find out how you can score distinction for chemistry on a consistent basis, either in our center or online via Zoom. If you want to check out my online school, go on to passwithdistinction.teachable.com. You'll be able to learn chemistry concepts at your own pace and anywhere in the world, topic by topic. This is Sean Chua from Winners Education, to your distinction in chemistry.